Okay, hello and welcome to our week 3. We are covering more machine learning classification algorithms. So if you remember last week, we talked about one of the basic classification models, which was logistic regression. And we also talked about one of the basic regression algorithm, which is linear regression algorithm. You noticed the similarities and the differences, and we focused a lot on the metrics and how these models are trained. So today we are going to double down on this effort. And from this point on, we mainly talk about classification problems, right? Which are the problems that are trying to, like the example here, you're trying to classify, ice cream from different types of ice cream. So you have categories. And for those of any question? Okay, and for those of you who have been here on 6040, some of the material here is covered there. So you are more than welcome to go back and refresh your thoughts on this. And for those of you who is seeing this for the first time, you can also take the pointers from myself or others to go back to those slides or but there are some commonalities. So it's a good time to refresh and strengthen your understanding on the decision tree support vector machine development. Okay?
Yes.
All right, let's go. So again, some of the slides here are derived from Professor Andrew Yang's ML course at Stanford, and some of the graphs are inspired by the book by Christopher Bishop, which is Pattern Recognition and Machine Learning. We're going to talk about, and actually that's a lot of topic for one course. So we'll see if we can get through all of it. We're going to talk about support vector machines or SVMs, decision trees, and ensemble methods. For ensemble methods, we build on top of decision trees, but ensemble methods are more general than decision trees. And just kind of a reminder that for notations, we are using small letters for scalars and vectors. And we are going to use capital letters, bold capital letters for matrices. All right. Okay, so let's begin with the notion of support vector machine. So we talked about this last session and also on our previous course, which is basically the idea of supervised learning algorithm, right? You are trying to find a line or a surface that would, let me just. Can you guys hear me?
Yes.
Yes.
Okay. So we are trying to, in all of these classification problems, we are trying to find a surface line that would separate the two, right? In the problem of logistic regression, the goal was to find a line that would maximize the probability, right? Remember, you're trying to maximize the probability. And the line that we derived there was trying to minimize the mean squared error for linear regression, right? So there are different objectives. Focusing on classification problem, logistic regression was trying to find a surface or a line or a vector that would identify the two-class in a two-class classification problem that would maximize the probability of each class. Support vector machines, or SVMs for short, are trying to find, again, another surface that would separate the two sets of data points based on another criteria that we're going to talk about, right? So we're just trying to, and this gives you a very, in few short slides, you will find how these two are separate, how logistic regression and SVMs are different from each other. There is a mathematical understanding to that I'll try to cover that. But I'm also trying to cover and provide a pictorial version of it as well, right? Not to get into the math of it a lot. So it's good to pause here for a minute and understand, starting from the basic classification problem, which is logistic regression, all the way to SVM, what is it that make these two different, right? Logistic regression that we fully covered last week is trying to find a line or a surface. Simply why I'm using a line, because if it's a 2D space, it becomes a line. You go to multiple space, it's a surface, or it's other shapes. That would maximize the probability of each class. Whereas support vector machine is trying to do something slightly different. So it's not about strength or weakness. They are trying to do different things. So for some application, logistic regression might be a better classifier. And for some others, we may prefer to use SVMs, okay? So again, these are hyperplanes. In 2D space, we call them lines. In 3D space, we call them planes. In general, we are calling them hyperplanes. They are either, the brown one, orange one, or the red one. They are trying to separate the blue class from the green class. And the goal here is to find the optimal separation, at least in the case of SVM, that provides the largest cushion between the closest points in each class. Okay, I'm gonna repeat this. So we are now focused more on SVM here, support vector machine or SVM. The goal for the support vector machine is to find the optimal separation, but unlike the logistic regression, the probability of each class is not the goal. The goal here is to find the largest cushion between the two classes. Okay, so largest cushion between the two classes. And between what part of the two classes? The largest cushion between the closest point in each class. So again, going by that, you can think of, let's say, this green to be like the closest to the rest of the space, right? One of these two, right? One of these two are probably among the green. In the class of green, one of these two are probably the closest to the blue. And among the blues, probably either this line, this one, or this one are the closest to the other class, right? From a Euclidean distance perspective. SVM tries to find the optimal solution separation such that it provides the largest cushion between the closest points in each class. Any question here? It's very common to have a question at this point, but
yeah, Professor. So among the three lines,
hold on a second.
Which line is the best one?
Can you repeat your question? Hello?
Okay, so yeah, which one is the best line in this picture?
I think we just mentioned that there is no best line, right? There's a criteria
yeah,
for which you select the line. The criteria for logistic regression was to maximize the probability. The probability of each class. The criteria for SVM is not maximizing the probability. It's finding the cushion, the line that would maximize the cushion between the closest points. So again, obviously the line here, let's say the magenta line here, obviously is not optimal. It's a very fixed line. One of the other two lines belong to logistic regression, and one of them, let's say, belongs to the SVM. Again, I'm just trying to convey what I'm trying to do last week and this week is that there is no best line here. You define the line based on the criteria that you define. In logistic regression, the criteria is defined is we are trying to maximize the probability of each class. In SVM, we are trying to maximize the cushion between the closest points in each class. Yeah, Niyati.
So Professor, when you say cushion, what exactly do you mean by the cushion between the closest points?
That's a good question. Yeah, we'll get to actually kind of see that. Let's get to that. What do we mean by cushion? So at least in the previous case, we mathematically understood that what is the probability of each class. And again, there is a. Let me kind of emphasize this point that the question of which line is better is obviously the wrong question. Okay, so you have to say what is the criteria for which you have a line, right? That's the. Now the second question is that okay, for what is the question that Niyati asked? Okay, what do you mean by the cushion? Well, which I will try to explain in the next 2 or 3 slides. But let's pause and go back to logistic regression. We repeated multiple times that the logistic regression, okay, let's go back for 2-3 minutes to logistic regression, try to see if we understood that because it's not that easy or obvious. We mentioned a couple of times that in logistic regression, the best line to separate the two classes is trying to maximize the probability of each class, okay? What does that mean? You guys going through this, can someone explain that? Okay, then what does that mean? So the question is on logistic regression, and we spent, and let me actually pause the video here because now that we know what logistic regression does, let's go to the question Niyati asked, is it, okay, what do you mean by the maximum cushion? Again, I'm assuming that at this point, you have some understanding on how logistic regression finds the optimal boundary. The optimal boundary for logistic regression is specific to logistic regression. The optimal boundary to SVM is specific to SVM. For some problems, SVM happens to be a better way of solving the problem. For some others, logistic regression is. There is no best or worst. And you looking at this and making an assumption is the wrong way of solving the problem. Either of these 3 lines could be good for a specific metric. I'm just trying to understand there is no right and wrong unless you define a metric. This is slightly different than a typical algebraic mathematics that we are familiar with. Okay, now let's go to the SVM. So the goal on SVM is to find the largest cushion. So cushion is slightly less mathematical to show. So we might have an easier job visualizing this here compared to logistic regression, I hope. So let's look at the picture on the left. We are looking at class 1, the red ones, class 2, the green ones. Do you think the dotted bold line is a good separator in terms of maximizing the cushion for the 2 classes? And again, what is cushion? Well, the cushion is that you are trying to what to do? You're trying to find the closest point of each class and then separate them so that it has the maximum distance from the 2, right? Because of that, obviously, the line should neither be close to class 1 nor close to class 2. So at least in terms of these two lines that are kind of parallel, the one that is less bold is more optimal. Again, in terms of providing the more cushion, there is no general global optimality here. You have to define what you mean. So at least on the left side, you can say that there is more cushion to these points on aggregate to this line compared to the bold line. And you can obviously say the same thing for here, because this provides more cushion. There's no cushion here, right? In the bold line, there's no cushion here, and there's no cushion here. Again, the bold line might be your logistic regression. The bold line might be your logistic regression. It may maximize the probability, but it doesn't maximize the cushion. Whereas, and again, there is no best or worst. You have to go to the application. And in the case of cushion, you prefer the light blue line. So here we are looking at some optimal boundaries versus some non-optimal boundaries. Question? So the two lines that are very close, or kind of, let's say, that touches the boundary, right? The dotted line that touches the closest red point to the blue points, and the dotted line that touches the closest blue points to the red points are called support vectors. So you have two support, and that hence the name of support vector machine. So you find the two support vector, and then try to find something in the middle, and that's your support, that's your optimal line. And you see, I think going to maybe if you go to previous courses, I try to introduce a more mathematical introduction. Here I'm trying to introduce the less mathematical introduction here. For SVM, if someone, you can find the right one by really looking at it, right? So if someone says, these are the points, can you draw the SVM? You should be able to draw it approximately, but closely. But if someone said, can you draw the logistic regression line? You said, no, it's a very mathematical heavy formula. I have to draw the formula. I have to optimize the formula. So one can really go through an ML interview and fail right here by not knowing these two models do. So you find the two support vectors, and now you should know what these dotted lines are. Pick the one that provides the biggest margin. Cushion is the margin here. The biggest margin of separation between the closest points of neither class. This minimizes the risk of overfitting in terms of misclassifying the points near the border. So it does some overfitting protection in form of misclassifying points near the border. So the line that maximizes the minimum margin is a good bet, and it's called support vector. It will be useful computation if only a small fraction. So basically, and you can see here, these points are playing less of a role. The points on the very farther side, or the points that are not close on the support vector, are playing a less of a role in where this margin line is going to be, right? Whereas if you go back to the logistic regression formula, every points are playing a role. Again, those roles are they're not, again, one of the things about machine learning is that not every point is playing a similar role. Some points inherently will play a more stronger role in where the boundary is going to be. So just to summarize here, we find the two support vectors. You can call one of them negative hyperplane, positive hyperplane, or the support vectors, and then you find the maximum margin across those. There's a lot of mathematical behind this, but I'm just kind of surfacing this for the sake of this conversation. The plane that has the maximum, again, because you can go to 2D, 3D space, we call them plane. The plane that has the maximum distance from both of the classes is the so-called SVM. Now let's get to the not that much of a pleasant part of it. What is the mathematical intuition behind SVM? So I'm gonna really quickly go through this because all the the audience are kind of interest. But the idea here is that when you have a vector is explained by, if you have two vectors, A and B, you can project one vector on the other, right? So if you have A and B here, the part here is called the projection of A over B. So A, the absolute, the magnitude of this vector A times cosine theta is the projection of A on B. Okay, that's just the magnitude, and this is called the magnitude of vector A. Actually, this has to be A. So one other thing that you do is that how do you really do SVM, right, on reality? So you want to know whether the random point X, let's take a random point X, okay? And you want to know whether the random point X lies on the right side of the plane or the left side of the plane. So how do you know if this point, without really looking at it, right? Think of a n-dimensional space. How do you know if it's on the positive side or negative side of the plane? How do you do that? So what you do is that you are assuming that X is a vector. So every point is a vector. And you then find, and then you have this plane, this hyperplane, blue hyperplane. And then you find a vector W that is perpendicular to the plane. So what is W? W is a perpendicular vector, goes from the origin to the plane, and it's perpendicular to the hyperplane, and that's called W. And then you have your vector X. And then you find the projection of X on W that you know how to find. So again, let's say the distance of the vector W from the origin is C. And now we want to take the projection of X on W. So you do W transpose X equals C. If this is positive, or let's say if this is larger than C, you have a positive sample. So basically you kind of divide this into two spaces. On one side, this number is larger than C. On the other side, this number is smaller than C. And exactly on the hyperplane, this number is equal to C. So this is where you have the negatives. This is where you have the positives. And this is where you're exactly 0. So W is a vector normal to the hyperplane or perpendicular to the hyperplane. And B is your, so basically this is your classifier, right? This is your classifier. Your classifier is WTX plus B. If this is larger than 0, you are going to assign it to the green class. If this is smaller than 0, you are going to assign it to the red class. You still have a cushion, and that's a good thing. You like to have a cushion. So if this number is larger than 0, you are going to assign class +1, and this is class -1. Okay. Now let's kind of just, any question? Okay, let's just revisit the notion of margin support vector machine. So if you notice, and that's kind of like, if you notice, you have a margin here, right? So technically, from this point on, everything is 0, right? And from this point to the left side is negative. But any question?
No.
Yeah, but there is a cushion where there is no point, at least from the training data set, right? So you typically actually have a cushion D. So you have a cushion like, so this is where WTX plus B is equal 1. This is where your WTX plus B equals 0. And this is where your WTX plus b equals -1. And at least from the data set, there's no point here, right? If you're looking at the perfect scenario. So you really have a cushion of d here. So the goal here, actually, how do you find this line? The mathematical objective of SVM is to find the blue line that would maximize d, right? So think about the cases where you have some green dot points here and red points here, right? It's not always perfect. This is a perfect scenario. It doesn't require SVM or logistic regression. You can simply draw a line and say, hey, this is green, this is red. But in an optimal scenario, in a realistic scenario, you may have points kind of interleaved, right? So there is no real cushion with no interference, right? There are always misclassifications or noise or actual bad data here and there. What you do is that you find, then you need the mathematics of it. You need to find the line that would maximize d given all of this. So you can think of the following. Let's say that they're parallel lines. These are parallel. They're all 2x plus y minus 2 equal 1, 2x plus y minus 2 equal 0, and 2x plus y minus 2 equal -1. This is the hyperplane on the right, left, and all, okay? Now, multiply the equation by 0.1, you would get this, and then multiply the equation by 10, you'll get this. So the parallel lines here, which are the margins, depend on W and B for our hyperplane. The line will definitely move as we change W and B. You're trying to different W's and B's. So you're trying to actually maximize this until this D changes until this D is maximized. This small d of the margin is maximized. And understand, the more we go to the mathematical part of it, it becomes less tangible compared to the non-mathematical explanation. Any question here? Okay, now a fair question is that, okay, you showed us the optimization function for logistic regression, and you're interested, hypothetically, on the optimization function for SVM. What's that? Because that's actually what, when you run the SVM classifier in scikit-learn, that's what this function is getting optimized over. So what is the constraint here, right? Because let's go back to logistic regression. The constraint here is that you're trying to minimize cost by changing W's. What is the cost here? The cost here is you calculate the distance d in such a way that no positive or negative point can cross the margin line. For all the red points, you prefer WTX plus b to be less than -1. You see, there's a margin here. You don't go by 0. Again, for all the red points, that's your criteria. For all the green points, that's the criteria. Now, for every point that you get, the goal here is to find the W and B such that these two conditions are satisfied. If they are not satisfied, you get some penalty, you add them up, and then there is an optimization function that does that. For every point Y, you multiply it by WTX plus B. Again, your goal is to find the optimal W and B such that these two conditions are satisfied. You have these observations, Y, I, that you can multiply by WTX plus B. This time, if you get larger than 1 for a positive class, that's good. If you get smaller than -1 for a negative class, that's good. Otherwise, you have a penalty. So actually, you are even penalizing if you get a green point here. You see that? Even though getting the green point here is good, you are still penalizing it because it's within your margin. So you are interested in having all the green points above the dotted green line, and you are interested in getting all the negative points below the dotted green lines there. And you are going to actually emphasize that this is your constraint. So you're trying to maximizing by doing so, you're basically maximizing such that this constraint holds true. And well, this is just the interpretation of that. You just find for each point x1, you find the support vector for negative class, and you find the support vector for positive class. Then you need to find the shortest distance between each of these 2 points. In this case, it's going to be this line, and you find this vector, and then you multiply this. So, and then you repeat this for all the points. Okay, so this is for now enough to go over the mathematical optimization function. The next thing on SVM is the kernels. Remember when we had logistic regression, how did we make logistic regression a little bit nonlinear? You remember? So logistic regression, what was that? It was A1, X1, plus A2, X2, plus A3, X3, W1, X1, W2, X2, all of that. That was the logistic regression in the most linear format. How did we went from a linear format to a nonlinear format in logistic regression? That was a long time ago, so let's see how did we do that. The example actually was probably linear regression, but the two are similar. So there we decided to go with x2, x3, x to the power of 2, x to the power of 2, right? So in logistic regression, when you go from x1 to x1 squared, x2 to x2 squared, you go from a linear relation to a nonlinear. And you can do the similar thing here with kernels. Kernels are trying to go from a linear format to a nonlinear. But let's go to a look at example. If you look at the data on the left side, it's a one-dimensional data, right? So x1 is some number here. Can you find a linear way to separate these two?
I can't.
So if you draw a line here, what would happen? Let's say this is x equals 0. If you draw a line here, actually you have a lot of error, right? Because you have a mix of the two here. But what if I say this is like x, okay? So x equal -1, -2, -3, -3, -2, -1, 0, 1, 2, 3, 4, right? It's just like, what if I said, no, just simply look at x squared. Okay, look at x squared. Do you think now the x squared would look like something like this? Basically, what happens is if you do x squared, but if you do x squared, then let's say this is this is +3, this is -3, right? So all the points above 3 and below -3 are now going to this x squared of 9, right? So they become like outside or inside. This probably has to be outside. Let's think of that. It would be better if these were greens and these were reds. But if you go to x squared, now you can simply separate the two, right? If you just squared every number, you can separate them. This is a very simple example to tell you that you cannot do linear solution. The linear solution is not optimal. However, the nonlinear solution is readily optimal. And you would do this with x squared. You do this with the so-called kernel. So basically, it's just the same thing, just a nomenclature here. If you do a nonlinear, if you apply nonlinear transformation from this, you'll get this, and then you can separate them. These are called kernels. Again, how do you separate this? It's very hard to separate them. You have to put this, you have to draw a line here, right? Which is obviously nonlinear. But let's say you find a circle, but let's say you convert them from this area to this area. The conversion is basically trying to go from a lower dimensional space to a higher dimension using some quadratic function. Now, if you go to a quadratic function, right, let's assume this is x1, x2. Obviously, x1 plus x2 is smaller for these values. And again, think of that. If you want to really like, how do you, let's actually get a little bit hands-on here. In this example, in the example on the left, how do you find, what is a circle? What is the formula for an equation of the circle that would, let's assume it's a circle, okay? Let's assume it's a very nice shape of a circle. All the red dots are inside the circle, and all the the green dots are outside of the circle. Let's assume that the x-axis is called x1, or actually let's go with x1. So the first question. This is for those of you who may or may not, you know this is a circle, right? X squared plus y squared.
Yes.
Let's actually stop here. Let me pause the recording. This is the part that. Oh, interesting. So this is the circle centered around 0 with radius c. Now, what is this one? This is a circle centered around x1 and y1 with the same radius. So if you find this point here in the middle and call it x1, y1, this gives you this. So you have a transformation. You have a nonlinear transformation. You have a nonlinear transformation that takes you from this mapping to this mapping. And then you can simply say anything beyond this circle or rectangle is class A, anything inside it is class B. But that happens because you are luckily, or there is some software or function that gives you the circle, and then this becomes a very linear function. After the transformation, you have a very simple space to talk about. These are called kernels. These are called kernels, and that are helping us make SVM nonlinear and make clear boundaries that divide the points. Okay? So you have a lot of kernels that are hyperparameters to your classification function that you have to try and see which one will help you better classify these two things. So a person using SVM to solve a problem would really try most of these kernels and say, hey, this is my F1 score with this kernel, this is my F1 score with that kernel, hence this kernel happens to be better. Then you can obviously try and justify or better understand why a certain kernel can help you. But listen, because on our projects, we are simply solving a multi-dimensional problem, they're not always as easy as this. These are just ways to explain to you what kernels are doing. Normally, it's very hard to go to a 10 feature and try to understand why a certain kernel does better. There are ways to explain this better or give you some vision. You can maybe visualize one feature versus the others, that kind of thing. But if you have 10 features and 3 classes, you can appreciate the complexity of the problem. Now, before basically going to decision tree, if you take 2 things from the two slides, let's compare them. In a logistic regression problem, you have a linear decision boundary, right? But in SVM, you may have a nonlinear decision boundary. In general, it's obvious that SVMs are more complex. And because of that, logistic regressions are more interpretable because you ultimately get weights, right? A1, X1, you don't get weights here. So you can go say, hey, it looks like that my weight on W1, X1, W3 is larger, so my third feature is more important. You cannot do that here. Hence, make SVM less interpretable. Again, because you can interpret the feature weights as their importance in logistic regression. But you cannot do that for SVMs. Oops. Okay, that's one way of comparing it. Now let's go to another way of comparison. That's derived from Andrew Yang's slides. So let's assume that you have n number of samples and m number of features. You have some guidelines on where to use what. Again, these are not written on stone, but this can help you. If you have too many features, to the extent that they are even larger than the number of samples, you don't get to these cases a lot, but let's say you do. You have too many features such that they are even more than your sample. Then you can use logistic regression or SVM without a kernel, which is a linear. If you don't have too many features and n is somewhere in the middle, you can use SVM with Gaussian kernels. If you don't have too many features, but you have a lot of data, you can obviously create or add features or use logistic regression or SVM without the kernel. So this gives a guideline. Again, why and what of this is beyond this conversation. But this gives you some guideline as to where to start. Again, you may find on some examples that these do not hold. They are not proof. There's no complete proof of it. There are some practicality behind this that would make you, start from some data points, but you obviously have to explore other scenarios. Okay, I'm gonna stop here, take a break, and then we will start with decision trees. Any question? Might be hard for you guys, but it's really, for some reasons, it's kind of elevate the motivation on my side. All right. The second part of this session is about decision trees. This part is actually very similar to what we covered on 6040. This is one of the other classification problems that we are interested in. There are many, and then we build on top of those ensemble methods. So we get to random forest and boosting algorithms after decision trees. So normally I'm talking about slide 34 all the way to 90. So I may skip a couple of the slides, and then you can either go back to our last course sessions or I'll skip through. There are many examples, so I'll probably try to skip through some of them. So the idea of decision trees is basically to use the features to ultimately split the variables into groups and get to some sort of a homogeneity within each group. So the example that I normally go by is this example of, is the person fit or unfit? And let's say the features that you have is the age, which is a numerical feature, whether the person eat pizza or not is a categorical feature, and whether the person exercises or not also categorical. So we are dealing with 3 features. 2 of them are categorical, 1 is numerical. And if you were to really tackle this problem outside of this machine learning era, if you give this to a non-technical person and say, can you figure out a way, an optimal way of finding whether the person is fit or not by these three features, I'm assuming the decision tree version of the solution is the approach that the person would take. So we would start by asking some questions and looking at the data and asking some questions, you know, like a 20 question type of games, and then get to the thing. The thing here is that you will probably also start by asking the most important questions, right? The more general questions, and the questions by which the answer gives you some sort of a more certainty. So, right, you're here very uncertain, and you would like to become more certain, and you would try to get to 100% if you can of certainty, which we call homogeneity, right? So you prefer that after these questions, every person who is less than 30 and exercise, or most of the person are fit, right? So you prefer that as you get lower and lower in this, deeper and deeper into this tree, you get more homogeneity, meaning that you get more fit people in this branch, in this leaf, than less fit, or vice versa. The pros of this method is that it's easy to understand and visualize. If you have multiple features that are correlated, this could handle very well. Whereas, you know, regression would solutions have some challenge dealing with this, and it would handle. You see, there's no nonlinearity type of an issue here. The problem is that you can get overfit by going too deep. And if your data set is also not balanced, you have problems. So let's get to more detail here. Again, another version of looking at the salary, commute more than 1 hour, or offers free coffee or not. Like every other machine learning algorithm, you have a classification problem. You can have classification problems where the output is a discrete variable, or regression problems where the output is a real number. Some terminology that we use here, we call the first node root node. We call this process of going to multiple decision nodes, splitting. Every time that you stop, and now we will talk about where do you stop. Every time that you stop splitting, you have a leaf or a terminal node. Every time that you don't stop and you continue, you have a decision node. So you have also branches and subtrees. Any question? So let's say you have two variables, features, x1 and x2. Okay, and you would like to create a decision tree that would split zeros from ones. You see there is this green decision boundary. So question 1, is this a linear boundary or not? If you were to draw a boundary, you would simply draw this boundary, right? Forget decision trees for a sec. Is this a linear boundary or is this a non-linear boundary?
I think it's a non-linear boundary. It's
non-linear because basically you are a linear is just if as you grow x, y should also grow. That's not the case here. Okay, now let's translate this into a decision tree. How would you, given the boundary, then how would you go? So the main thing is that you have x2 and x1, right? There's nothing more. So you have to split by x2 or x1. So the first thing is that you can say, hey, I'm going to split by this line first.
So it says x2 is less than 3 or not. If x2 is less than 3, I get this left side and the right side, right? So you get this guy. And then if x1 is larger than 4, so if x2 is smaller than 3, if x2 is smaller than 3, and if x1 is smaller than 4, you're here, right? It's all zeros. So this first couple of splits gives you all the zeros here. Perfect homogeneity. If x2 is smaller than 3, but x1 is larger than 4, you get this guy, also homogeneity. And you have to keep going. So you see how it goes, right? This is clear that's what it does. Now the question is that is this the optimal way of doing it or not? Should we really start by asking x2 smaller than 3 or not? So can someone tell me, and again, may not be the easiest question here, that is this the right way to start with x2 smaller than 3 question on the root node?
I think it's not the best way.
Why?
If you go with the 5, then it would be better in terms of zeros point.
5?
Yeah, x2 equals 5.
X2 equals 5 gives you
x2
1 here. So yeah, okay. Instead of 3, go by 5. Hey, you're saying that if you ask x2 larger than 5, that's all ones here.
Mm-hmm.
Yeah, and actually, I don't have an objection to this. But it's the right way. Actually, it might be the right way. So now let's see. Okay, well, actually, this raised up the question. Okay, how do we really split? Because neither the way this guy has approached nor the way that Hijai approached, we don't have a quantified version of measuring this. And we need, again, unfortunately, mathematics to help us here. So you have to find the best decision for the root A node for the root node, and then continue finding the best feature. And it's not just the best feature, it's the best feature that gives you the most homogeneity and all of that. So how do we choose which attribute is the best? So there are multiple ways to do that. Again, gives you more things to tune. And they're not best or worst. You have to find a metric that gives you the best split. And these are so-called impunity measures. So you have a Gini impunity, information gain, and misclassification impurity. I'm going to explain at least one of them so that you get a sense of it. So at each node, you have to go by one of these and then split. Okay, let's go by Gini impurity and see what it does. The Gini impurity is the so-called I, which is 1 minus the sigma of I equal 1 all the way to j pi squared. What is I? What is j? The j is the number of classes present in the node. So you may have 1, 2, 3 classes. And p is the distribution of the class in that node. So if all, so that basically this number and you'll see in a sec, it could be 0. If you get to the case where all the cases in a node fall into a single category, which is the best. Or it could all go all the way to 0.5, which is the worst, which you still have equal ambiguity. At each step, you select the feature variable that has the least Gini impurity. I'll go by one example because that would clear stuff for you. And probably we can skip the rest of it because there are very similarities. So let's say that you are trying to focus on 3 features only. So among these all the features, just we pick sex, fasting blood sugar, and exercise-induced angina, exang. To predict whether the target is yes or no. Okay, so it's I forgot what the case is, but whether there's a problem or not with the yes or no. Okay, so the question is that which of these 3 features should I choose to start? That would give me the max, the minimum Gini impurity. And you have 2 classes, right? Yes and no. So basically that sigma is going to be over no's and yeses. We'll get to that. So just wait, forget the formula, but you can also use the formula. In order to get, and again, by the way, we all have target yes here. So yeah, this problem. Yeah, let's go to the actual example. So I think I probably need the okay. So let's say that you are choosing sex to split. And let's assume that you have, if you split by sex is easy because you have 0 and 1, right? That's if you have 138 no in the no class and 165 in the yes class. Let's assume that if you split by sex equal 0, you'll get the following. And if you split, and the other branch would be this, right? Again, the total of 93 plus 114. There's some miscalculations here, but give me a second. This is not. So again, like I said, the number of yeses here plus yeses here should sum up to this. But for now, let's focus on the blue numbers in the blue boxes. Okay. So let's assume that if you split by sex, you'll get this distribution on the left and this distribution on the right. Okay. What would be the impurity, Gini impurity on the left node? So it's 1 minus 24 over 24 plus 114 minus 2. Basically, this is the summation of this, right? This is the probability of no, and this is the probability of yes, okay? And think of that. If you have all yes or all no's, this number would be 1, you get 0, 1 minus 1, 0. And if you have 50-50, this becomes 0.5. So it could get as low as 0, as high as 0.5. 0 means no ambiguity, all purity. 0.5 means all ambiguity now. So the impurity on the left node is 0.29, not bad. The Gini impurity on the right node is 0.49. It's actually very bad, right? So on the right node, you have you have not gained that much. Left node is good. And then you have to do the weighted average of the 2 nodes. you have 138 on the left node. So on the left node, it's 138 over 138 plus 165. And you have 165 here, which gives you so basically this is, again, just to kind of, this is the Gini impurity of the left node. This is the Gini impurity of the right node. And then you have to do a weighted average of the leaf node impurities, which is basically that you have to go by how many nodes that you have times the impurity of the left node and how many yeses you have impurity of the right node. And if you do that, you get 0.399. Okay, pocket that. You have to repeat this if you go by fasting blood sugar. Okay, if you do all of this, assuming that you get the distribution here and here, you get to 0.249, which is better because it's lower compared to splitting by sex. And it's kind of obvious. You get 116 here, 22 here. It's all, here's the thing, you get all nodes here and you get all kind of nodes also here as well. So you get a good balance of impurity on these two nodes. And if you do by hexang, you get 0.399. So to compare them, you ultimately find that the Gini impurity is the lowest if you do by fasting blood sugar. Yes, Ned.
Professor, I do notice that when we take the total of the left-hand side, 116 and 22, that comes down to 138. So is it the FBS saying yes and no, and below that no, talking about the target yes and no? Is that
So
what the slide was
saying
meant
that,
to say?
yeah, you're saying that 116
Plus 22 will give
gives you
138.
138.
So that
Yeah.
is the no for the FBS, and the yes for FBS is 165. And then we split that again, and then we get 142 and 23, which is the total 165.
Okay, what is the question?
So in the beginning, you said that this is target no and target yes, right?
Let me start from the sex. Okay.
Yeah. So
Okay.
should it be like sex? That would be no and yes, and the no's are 138. And when we split that, the target no and yes would be 24 plus 114, which again gives back 138.
Okay, so these are, if you split by sex,
Mm-hmm.
within the sex equal 0, female or male,
Mm-hmm.
you would have
Those indicate,
140.
yeah. So probably it's just splitting 138 and then deciding whether the target is a yes or no.
Okay, so yeah, but I guess your point is correct. What is kind of probably misleading here is that here, if I were to put it like, let me just find the right in the, actually let's stop there. Okay, in the line, let me choose the scribble. So then this is probably if I understand correctly, we shouldn't have the yes and no here, right?
We should have only
Is-
yes and no. We shouldn't have target over there because under the sex there is either
Yeah,
male
yeah.
or female, and
Yeah, so
out of those
basically,
males we'll have the target.
exactly. Okay, so if actually, let me see if there is an annotated version. Yep. If I were to create, this is not the target.
Hmm.
These are the number of sex equals 0. And this is the number of sex equal 1. Within the sex equal 1, we have this many target yeses and nos. And within sex equals 0s, we have this many yes and nos, right? That's the, okay, yeah. Thank you, yeah. Thanks for correcting it, because I actually, all right, let me actually take a note of this. This was, yep, that's exactly correct. So I'm actually gonna, oops, I'm going to erase all. Yeah, so I think, yeah, and that's the right thing to do. Let me actually take this and put a line here. This is probably not the right. That's probably the right way too. Okay, I'll take a note of it. So yeah, it's not the target yet. So if we split by sex, and actually that should be easier to simple. If we split by sex, we get 138 samples on the left side, 165 samples on the right side, and that's the distribution in yes and no's within those left and rights. And looking at the gene impurity here, we have 0.39, we have 0.24, and then we have 0.39. So we are going to split by FBS for this example, right? Okay. We are going to split by FBS if we choose gene impurity. So you can go back and say, hey, I want to do by information gain. You may end up splitting by something else. And again, these are your 3 hyperparameters to tune here. So let me actually try to wrap this up. We split by FBS on the first one, and we end up with whatever we get. Then we have 2 nodes, and then we have to start computing what to split on. And we may even need to do by split by exanc or something else and continue doing this, right? So I'm gonna actually stop here. So let me see if I have the animations here. So you do by FBS and you get to here. And then on this, so you have a left node and then you have the right node. And then you have to decide what to do with the left and what to decide to do with the right. You may again need to even split by FBS again. Again, that's probably less of a probability. You continue doing this. So, and then you end up with this version. So you see FBS, exanc. We decide to stop here, right? So that's one other thing. We decide to stop here and then we go and then if you repeat this, okay, let's say you repeat this, okay? Let's get to the end result. You split by FBS based on the minimum gene impurity. You have some distribution on the left for which you decide to do exanc, and then you decide to do sex here, and you continue. Okay, the main question here is where should we stop? There are a couple of obvious reasons. If you get to 8-0 or 30-0, you will stop, right? That's obvious. There are other situations that you may also need to stop. If you keep splitting, you will overfit. So you maybe decide to say, hey, with 92 and 3, 92 yes or 3 no's, or vice versa, I'm gonna stop. So and then you may also like, sometimes it go back and prunes it. So the algorithm behind the scenes may decide to stop and then, or even sometimes go back and prune it. So you would like to go as deep as you want, and you do not like to go as deep as you want based on overfitting. And again, I don't know if I have slides, but you can also go back and define what is information gain and what is misclassification impurity, and you may have a different decision tree. But what is overfitting and underfitting? With decision trees, it's easy, right? Let's go to the overfit. If you have a large number of features, so hold on a sec. Any question? This is a very generic slide. It's not just for decision trees. It's applicable to every machine learning algorithm. The more you have, the more number of features you have, or the more complex model that you choose, you're going to overfit. The result is your test score is going to be much poorer than your training score. The less number of features you have, the less simpler model you have, you'll get underfit or high bias. The score would be poor for both train and test. What is the implication for this? You're familiar with, right? By now, this is your go-to graph for classifications and regression overfit. The one on the middle looks like something intermediate, where you don't neither underfit nor overfit, and you have the best regression model or the best classification. On the left side, you will have a high bias. On the right side, you have a high variance. So when do we get overfit? If you have not too much data, if your data is a small amount of data, number of samples, you're more likely to get overfit. You may still have noise here, errors in the data. You may have irrelevant features that could cause overfit. So here is a good way of looking at it. And I think you probably have exercised this last course on your 60/40. On the right side, on the x-axis, you have the number of nodes. Or you could have depth of a tree, right? So it could be number of nodes. Number of nodes or depth of a tree. These are the measures that at some point you start overfitting. It makes the model more complex. So as you can see, the accuracy goes higher and higher for both train and test. But at some point, the test set, which is the set that you are not training on, but you are evaluating on, starts to diverge from the training set. Your training result, almost every time that you make the model more complex, it's going to get better. That's the deceiving part. Whereas your training data, test data are going to show a diverging result. So probably you'd like to stop somewhere here. Every model that you train have multiple hyperparameters. Number of nodes, depth of a tree, whether you choose gene impurity versus, these are all the things that you have to tune over. Some of them would make the model more complex, less complex, or just different. So if you choose gene impurity versus information gain, neither is overfit. They're just two different hyperparameters. But this depth of a tree is a parameter that if you keep increasing, you're over. So you see, you have multiple parameters to tune over. So one other thing that makes a good machine learning project is where you show that your test scores, F1 or precision or recall, over a spectrum of hyperparameters. To see where do you get overfit, where do you get underfit, which one is even collaborating, cooperating towards that, which parameter doesn't have no effect, and you will never know which one is done. That's one of the kind of still mysteries. You still have to train on all of this and find the best. How do we avoid overfitting? You stop growing when the data split is not statistically significant. You acquire more training data. If you can, you should remove irrelevant features. Sometimes you grow the full tree and then you post-prune. That's another way of doing this. How to set? So let's say you can also train multiple trees, right? One with this depth, which is actually these are multiple trees, right? And then you pick the one that has the best validation performance or test performance. So you compare them based on their performance on the tests of validations. Okay. Talked about this. Talked about this. Okay, that's good. So let's take this time. I promise I'm gonna come back in 5 minutes. But yeah, let's take a break, and now we have we can continue with more breath to the second part. Okay, so this is also covered mostly in the 6040. Actually, I have to find the right balance between these two courses if I were to teach them again. But ensemble method is basically trying to, as the name suggests, go through multiple models. Eventually, any machine learning model that you train in reality is an ensemble. It's multiple models. If the task is huge, if you have a lot of data, you probably cannot have one model. You have multiple learners. Even if you add, any type of a thing, it's not a project level course, but for mostly realistic industrial type of problems, you need multiple learners, maybe a shallow model here, a deep model there, that kind of a thing. So these are called weak learners. And if you combine them correctly, you can obtain a very accurate and robust model. The way you kind of combine them is the ensemble. So this is our infamous chart of bias versus variance versus model complexity, and where does the optimal point stand. The idea of this weak learner is actually the same thing. You're either training multiple very high bias weak learners, or you're training multiple very high variance weak learners, but on aggregate, they're really good. That's one way to get to this point. So far, you were trying to use the hyperparameters to find this point, and you will do that. But an alternative is to do ensemble. Don't care about whether they are high bias. You should still need to know whether they are high bias or high variance. But then aggregate, this problem is resolved, and you end up somewhere here. So you are not tweaking the model complexity per se, but you're doing ensemble learning and solve this problem. So you can either have a model, so a weak learner is either a high bias model, and you know what's a high bias, it's just a very simple model, low degree of freedom, or you have kind of a high variance model that has a lot of parameters, too much is overfit. So your goal is to reduce the bias or variance of these weak learners by combining them and creating a strong learner at the end. So that's just our way of going through this. There are multiple ways to combine these models. And you'll see why the name, but you can ultimately, they go either under the bucket of bagging or boosting, or a combo of those, which is stacking. In bagging, you have homogeneous weak learners. They all are the same. They learn independent of each other. They're learning in parallel. So you can see that you can expedite the training. And then you combine them by some sort of a averaging process or majority voting. Let's say you train 10 weak learners, and if 9 of them or 8 of them say yes, you'll go with yes. In boosting, and they're all, let's say, decision trees, or they're all logistic regression. But mostly this is very well designed for decision trees. So you can put multiple decision trees, train them independently, and on aggregate and on ensemble get a good model. Another approach is boosting, where you do not train them in parallel, instead train them in an adaptive sequential way, meaning that you train one of them, and then based on the result of that, train another one, and then based on the result of that, train another one. So you have to do it sequentially. Obviously, that will reduce the speed, and then you combine. And this third category that we're not covering here because it's a very open way, that you combine logistic regression with a decision tree and all of that. It's very open. We would like to cover these two, and this was already covered in the previous course as well. Any question? Okay. So in the bagging, you are creating a bunch of weak learners, and the ultimate result is going to be less variant than its component. So actually, that means that in bagging, you train multiple high variant models, and you would create, but the ensemble happens to be less variant of each individual. In boosting and stacking, you still have multiple weak learners, but they are highly biased, and the goal is that you reduce the bias. As a result, you may also reduce the variance, but the way that you do the bagging is more inclined towards reducing the variance, whereas the way you do the boosting is more inclined towards reducing the bias. So it makes sense to have high variance models here and reduce the variance of the combo. And it makes more sense here to have highly biased models here and reduce the bias of it. Basically, the bagging technique by itself has this tendency to reduce the variance. That's why you can have high variance models in there. And the way you do boosting mathematically tends to reduce the bias. That's why it's okay to have high bias models in there. Question?
So, Professor, just to simplify this, we can say that if there is a model which is kind of overfitted, so it will have high variance, so we can apply bagging to an overfitted model. And if it is underfitted, then we can apply boosting or stacking to an underfitted model.
Yeah, it's one way of explaining it. The other way is that, okay, if you have multiple decision trees,
Mm-hmm.
and they are
so maybe if we take, say the data set has 10 features, but we select any 3 for a particular decision tree. So 3, 3, and 3. So all those 3 decision trees can be ensembled into a boosting and stacking method.
Yeah, but why not the bagging?
Because if out of 10 we probably take only 3, there is probably more bias.
So yeah, basically, yeah. And again, yes, but the thing is, when you choose, yes, that's true. But when you choose let's say you do bagging,
Mm-hmm.
which is called random forest, it would implicitly inside that are gonna choose models that are high variance. So they could still have less features, but they are very deep.
Oh.
So the way, if you choose to do the bagging, So it's not that, like, from a logical stand, it's not that you have some
Mhm.
models and then you start what to do with them.
Mhm.
You decide what to do, and then you start doing the design is not like you have a bunch of bad models. They are either high variance or high bias. Now, how do I bag them or boost them?
Mhm.
You decide to do bagging and boosting, and then you do a top to bottom design. So you said, okay, I'm trying to do bagging. I prefer to do bagging of decision trees.
Mhm.
Then it is better to choose model decision trees that are highly variant, means that they're overfit.
Okay.
How do you overfit a decision tree? You just go very deep. You end up with having multiple very deep decision trees. So the
Oh.
logic of design is not that you have some very bad model and then you say, okay, how do I improve them? You decide to
So
do bagging or boosting from the get-go.
right. So this is basically not a way to optimize an existing model. That's the crux of it.
Yeah, you can do the optimizing some existing model, but normally, yeah, it's better to just design what you want to design from the get-go. Underneath, and again, you never decide, you can tune the parameters of a bagging decision tree, which is random forest, but you never really have to go there and design each of those smaller decision trees inside the random forest. It will just do the job for you.
Okay.
Yeah, good question. Okay. Okay, now let's start with bagging. Basically, in bagging, we decide to have highly variant model, overfit model, and reduce the variance. Okay. Let's go with this. Okay, so there are things that we do. The examples are more applicable to a decision tree. So a bagging version of decision tree is called random forest, but you can do it for logistic regression, for SVM, and all of that. But how do you, okay, then how do you do that? How do I design these weak models? And that's where it goes back to questionality. You don't have bad models. You create those bad models. Intentionally, you create those. How do you create those? Well, you have multiple models. You're trying to create multiple weak learners that are overfit. You have to first bootstrap your data. It means that you have to create training data for model 1, training data for model 2, training data for model 3, and all. It makes sense that your data kind of shuffles, right? You don't get all of your data to all of them. That's it. So with bagging, you bootstrap the data. It means that you sample your data and you feed it to model 1, model 2, model 3, model 4. And let's say if you have 12 samples, for instance, you get 5 of them to each model. Your model 1 gets to see only 1, 10, 3, 8, and 3 samples. It could have even duplicates. That's why it's a weak learner. One of the reasons it's a weak learner, because it actually has exposure to a sample of your data. That's called bootstrapping. And that's what you do with the first step in bagging. Is it clear? In the second step, so basically bagging is that's bootstrap aggregating. It's not really bagging. This comes from bootstrap aggregate. In the second one, so you first do a sample size of m out of n. Then you also subset the features. So I don't know if I have a good image of this. Yeah. So you not only subsample the data, you also get a random subset of features. So the model here not only sees 5 of the feature, 5 of the samples, but let's say you are trying to train a model with 10 features. The actual model has 10 features. Your first model is only have feature 1, 2, and 5. Your second model has only feature 1, 8, and 9. So you do 2 subsampling, one on the data, one on the feature. These are definitely weak learners, right? They are looking at the portion of the data and they are looking at the portion of features. But they get very specialized on those sub-samples and sub-features. That's why they are overfit. So you create a multiple bootstrap sample, and you also create a subset of features. So and then you aggregate or average the output. Averaging the output tends to lessen the variance of each one. So this is one way of looking at it. You subsample the data, bootstrap. You create multiple classifiers that on aggregate, they have less number of features to train on. And then you average the output. Again, averaging if the output is numerical, you average them. If the output is categorical, you just do the majority count. A bagging version of decision trees is called random forest. In random forest, you are training multiple weak decision trees. And here is the case. Actually, I have to kind of even substitute this because we are now talking about this, right? So for deep trees, so you have, the idea here is to have multiple weak learners, right? But high variance. How do you create a decision tree that is high variance? You go deep. Deep decision trees are overfit. They have low bias, but they have high variance. And they are good choices for bagging method, hence the random forest. If you do shallow trees, you tend to create less variance, high bias, which are good choices for sequential models that we have not yet covered. Okay, question? So you have two sort of, again, randomness in random forest. Random number of samples in each tree, bootstrap, random number of features in each tree. So this is just a good idea to give you a picture. So you have 5 features and 5 samples. Okay, look at the node here. You create multiple decision trees, but you see the model 1 on the very left only has X3, 1, 3, and 4 feature. It has 5 samples, but it gets to be bootstrapped. So you have 1, 1, 2, 5, 5. And you repeat this for 10, 20 trees. And then you get multiple deep, relatively deep, highly variant decision trees. And then you take the majority decision of the output. Sequential models, on the other hand, you combine weak learners, but you do them in a non-independent way, sequential. Each of these are highly biased. They're weak learners. They're highly biased. But the sequential format of it tend to lower the bias of the whole system. So thinking of decision trees, if you want highly biased, that means shallow trees. You need multiple shallow trees, but you train them in sequential. What does it mean to train in sequential? All right, that's the part of the one. Basically, training of this is slightly different. It's not in parallel. And let's look at this example. Let's I don't know if that's my slide. I had some very good slide. Yeah, okay. I used to have a better slide, but I'll probably stick to this one. So actually, give me a sec, see if I find, I think I used, I'm gonna go to the previous 10 slides and explain. So in the boosting, and this is slide 75 of the previous one, previous course, you decide to train them in sequence. What you do differently is that, let's say you decide a model, and forget decision tree. This is just boosting, okay? The first model, let's say you train this, okay? And you end up with something like this. It's a boosting. Think of a model, just forget decision trees. You're just trying to sequentially improve a model. The first model is something like this, right?
Mhm.
There's one blue point on the left misclassified and one orange point on the right misclassified, right?
Mhm.
Now that you are going to iterate, what boosting is going to do is that it's going to say, hey, I have made errors on 2 samples. Now, normally, when you train models, each sample has equal weight, right? Samples are equal. This time we say, hey, training the next model, give more weight to these 2 because I've already made mistakes on them. Give more weights to them. So you can see that it's going to tilt, right? That border is going to tilt because, and then you end up with this. Say now that you're going, now repeat this. So you repeat this by saying, telling the next model to give more weights to the samples you've made error. And you repeat this, you repeat this, you repeat this, all the way that you finish this. So each time you give more weights to the samples that you train. An example of this is something like that. Let's say you have feature 1, feature 2, feature 3, you don't care what it is. Initially, each weight sample has 1/5. Let's say you have 5 samples, each weight has 1/5. But you make an error on sample 2, whatever. Going forward, it says, okay, now give more weight to this guy. And as a result, because all the weights should sum up to 1, give lower weight to the rest of them. So it is clear that on the second iteration, it's going to make a better decision on this one because it has more weight. And you repeat this and you repeat this all the way. So let me go back to the slide that we have here. This is basically trying to say the same thing, visualizing. So you make a mistake on, let's say you're trying to just classify, and for whatever reason, this model makes a good decision on magenta and this yellow, but makes bad mistakes on the rest of them. So it's going to put more weights on those that it makes a mistake, and those that it less weights on those that it was correct. You can see that this is going to be up and down, up and down, up and down until it gets to a steady point, but it makes a good decision. So now you have a bunch of weak learners, and you can just average the output. This is called boosting. The boosting version of decision tree is called XGBoost or AdaBoost, a ton of them. And that's one of the things that when you're training a decision tree on a boosting, you have to train those. It actually happens to be very powerful machine learning models, boosting decision trees.
Professor, so the data, the training data is the same, but every time the weights are different. Is it?
So one other thing, one other thing that you do, the training data is, you can think of slightly more complicated because you can see that you can make a mistake. Actually, you would probably make less mistake on training, more on the test, right? So on the next round, you do need to do a shuffle, not a shuffle, random shuffle. That you're gonna see the mistake on the test, put the test into train, and put the train into the test, because you normally tend to make less mistakes on the train and more mistakes on the test side. So you need to multiple back and forth of data. So it's not, I don't think you can keep the train the same and test the same. You have to borrow from this, because on the test set is where you are seeing more of the errors. So yeah, I think the picture does not.
Adding back the tested data to the original trained data, we separate a new test, new maybe 20% of data for the next testing. Is that what you're saying? Something like that.
Can you repeat your question?
Yeah, like after the first training and then use it on the test, we put back the test data into the training data, and then we separate another maybe 20% for a new testing data and see the result. Something like
yeah, basically, yeah, because okay, what's happening is that you may not have, if you have actually, so here, if you have a lot of errors on the train as well, then yes, you can. And actually, these are, so to my point, these are less, these are highly biased models. So you may have actually a lot of those in your data. So you may not need to do the shuffle I talked about. So basically, to give you the full answer, you may not need to do the shuffle that I just said, and you just need to use the train data. You can keep the test as it is, make it, and just keep the test as it is. Use the validation set, some set in the middle, and borrow from that. Any questions?
Okay, so I was just saying that there are different ways of boosting. What I just explained is the simplest one. Giving more weight to the samples that you made error is the simplest one. There are many more. And actually, these are worth looking into if you're gonna really work in this domain. So just to picturize everything, the boosting is the bagging we talked about. You have multiple parallel models that are high variance over fit, and you tend to lower the variance by aggregating them. In boosting, you are training multiple models in sequence, and the aggregate, they are all high bias model. And this way of aggregation tend to lower. And I think if you go back to the previous slides that I had for previous semester, they tend to be more mathematical. So I encourage you to do that. And then stacking is basically you just, like, you have not, the homogeneity goes away. You can put a decision tree with an SVM and all of that. You may need to do that, but it's not very, the idea of stacking is basically you have these models do not need to be identical in terms of being a decision tree or logistic regression or SVM. But the data, and then you may have another model, but they see different. So one of the techniques actually used, if you notice from bagging and boosting, is that if you have multiple models, either in parallel or sequence, you see this has both parallel and sequence. You have some parallel model here, and then another meta learner here. It's better for these models not to see very similar data. So you say you shuffle the data into 70 and 30 or whatever, and some of your models sees all your data on it. This is actually, so for instance, one of the examples that if you're doing a recommendation system, right? Again, this is also beyond the scope of this course, but the recommendation system is that, let's say you want to, a Netflix version, you want to recommend 10 movies to a customer, right? How do you do that? Do you think, what would be the best strategy?
Use cluster.
Genre.
This idea of stacking is applicable in cases where you want to have a funnel where you filter data and then you sort them. Again, unfortunately, this course is not really going over recommendation. In recommendation, it's not about whether this is class 0 or 1. It is how relevant this data is to this user. And it's a probability number. But weak learners and kind of your deep learners, weak learners, you can use them at the beginning of the funnel. And the deep learners, you may tend and prefer to use them at the narrower part of the funnel. So with that, we are concluding today's session. I'm gonna stop the recording here.